All right, so we're looking at parts of a radical. So we got some fill-in notes. So the nth root of a number, a, can be written as the radical expression nth root of a. All right, so we're just going to start by labeling what's happening here. We've got some, maybe we've seen a radical before, but maybe we're not totally sure what all of the parts mean. So we're going to look at those different key terms in this video. All right, so parts of a radical, this guy up here, it kind of looks like, so actually let's just start with this symbol here. This is the radical symbol, this like square root, the radical. And then this number here, the n, this is called the index. And it kind of looks like, you can almost imagine too, it's like a waiter, kind of looks like a person like holding a tray, right? So that waiter is like holding that, that number. All right, and then the number that's inside the radical is called the radicand. Radicand, which I know is like, what? Like, that's a really weird word, radicand. We're also gonna call it the base because we're still in the world of exponents. So still thinking about it in terms of like a base to the power of an exponent, and that'll make sense on the next slide. But technically it's called the radicand. We're gonna be referring to it as the base for our class. If there's no index given, if it's just like rad 20 or something, then we could assume that n equals 2. So we can assume that the index is 2, meaning we'll have a square root. So if there's no index given, it means it's called a square root. The index is 2. And again, we're gonna dive deeper in understanding what even the index means, like what's happening. Or for now, just labeling different parts of radical. So if a radical has more than one root, the radical sign indicates only the principal or positive root. All right, so it's always gonna be positive. All right, we're gonna jump to our next slide. Make clear. All right, so looking at this slide, main ideas. So starting with square roots with variables, so unknowns with variables. So if we're given square root, right, because index is not, there's no number there. Square root of a to the power of m. If m is a multiple of 2, so if our exponent is a multiple of 2, this is the rule we'll use, or like the hack. We can always rewrite an exponent, or excuse me, a radical as an exponent. I got that backwards. We can always change a radical sign to become an exponent, and this is where I'm going to show you. So rad a to the power of m is really our base. Again, base is a, exponent. Let's note the index here would be 2 because it's a square root. So it's going to be m, whatever that exponent is with the base, divided by 2. So this is a key idea. We want to make sure this is in our notes. Key idea here is that the denominator is always the index. Denominator is always the index. Index always becomes the denominator. Denominator is always the index in terms of when we have an exponent that's a fraction. All right. If our m, our number inside the radical, our exponent inside the radical is not a multiple of 2, right? Multiple of 2, basically that means if we're given an even number, whoa, cannot spell even. Hold on. Okay, there we go. Even number, multiple of 2. If it's not a multiple of 2, that means it's going to be an odd number, right? Like 1, 3, 5, 7, etc. So we can break it apart. We can take that, whatever the exponent is, let's say it was 7, a to the power of 7. We can rewrite it to be 7 minus 1, so that's a to the power of 6 times a. So basically, by subtracting 1, we're making it even. So our goal is for it to become even, and we're going to see how that makes it easier when we simplify. All right. And this is one method to solve. We're also going to go over 2 other methods to simplify later in the video. All right. So first, perfect squares. List all the first 12 perfect squares. So we have gone over this for our Cougar math skills. Do you remember any perfect squares? If there's any that come to your mind, go ahead and message in the room chat what comes to mind when we're hearing perfect squares. Any numbers that come to mind, go ahead and answer. I'll pause the video. All right, so perfect squares. 1 squared is 1, 2 squared, 4, 3 squared, 9, 4 squared, 16, 5, 25, 6 is 36, 7 times 7 is 49, 8 times 8 is 64, 9 times 9 is 81, 10 times 10 is 100, 11 times 11, 121, and lastly, 12 times 12 is 144. These are the top 4 perfect squares we want to memorize, all right? Looking at these below, 1 through 4, perfect square roots. So I wanted you guys to try simplifying these on your own. Again, we have already gone over perfect squares, right? Taking the perfect square roots in past Cougar Math Skills, right? I think that was just last week even. But I want you to try these on your own. And then once you get your answer, go ahead and box it in Desmos, and then we'll go over the answers in a moment. All right, so I'm gonna pause, try that on your own, and then we'll look over the answers and compare. All right, so we're familiar, perfect squares, finding that value. I wanted to point out again, so perfect square like 16, that's 4 times 4, 4 squared, the exponent and the radical cancel, leaving us with 4. I'm gonna go over this on the next slide, why that is. It's gonna make a little more sense when we have more room, but hopefully you got one or a couple of these as your answer for your Desmos. All right, I forgot to also add this to our notes in Engagely, so I'll probably skim back, add this to your notes, and then we'll move on. Okay, oops, I went too far. Hold on, there we go. All right, so simplifying radicals, our first, kind of second method, because the first method was technically in the notes, where we were saying like if we have an odd exponent in the radical and it's a square root, then right we subtract 1 from that to make it even, and then just leave 1 behind. All right, so for here, simplifying radicals, this is the first method called prime factorization. Let me move the camera somewhere else. All right, so method 1, simplifying radicals using prime factorization. So step 1, this first method is called a factor tree method. So first thinking like, what does this mean? What's happening? It won't let me highlight over there, but room chat, have we heard of prime factors before? Maybe we have in Cougar Math Skills, but what do we think of when we think of prime numbers or prime factors? Is there anything that comes to mind, or even a factor tree? Have we heard of these before? Go ahead and let me know in Engagely in the chat. All right, so a prime number, remember there's 2 different words, so there's prime versus composite. So composite number has factors beyond 1 in itself, right? Like 4. Factors of 4 are 1 and 4, and also 2 and 2. Like 12, 1 and 12, 2 and 6, 3 and 4, right? Kind of like, remember we were listing out like the different factors of numbers in Cougar Math Skills a couple weeks ago. So a prime factor, prime means that the only factors are just going to be 1 and itself. If I can spell. If I'm getting too comfortable with Engagely for being able to go back. I can't do it in the videos I have to erase. Anyways, prime factor, prime number, 1 in itself. That's the only factors. There's no other combination we can multiply to get that number. So our goal is to simplify 12 in this case, rad 12. Simplify, break it down to its building blocks, prime factors. All right, factor tree, hopefully we're familiar with this or we've seen it before. If not, we're gonna go over it. So we make like a little tree. It's like you're making a little pine tree. All right, and you start off with what 2 numbers multiply to give you this number 12. So, right, I actually just listed out all the factors. I was gonna ask you guys, maybe we weren't paying attention, but go ahead and let me know in the room chat 2 numbers that would multiply to give us 12. That's not itself in 1. Not itself in 1. Because if we did 1 and 12, I'll show you, but not itself in 1. I'm also realizing this is a video recording, so I don't know what numbers you're doing. Hopefully we did, I don't know, maybe we'll just say 3 and 4. Right, you could have also done 2 and 6 was the other combination. 3 and 4. Now, when we're listing out all the prime factors, super important. I want us to circle the prime numbers. Circle prime numbers. You're like, Mrs. A, do we really have to add this to our notes? Yes, this is so important. So important. Add this to your Desmos too. Circle the prime numbers. But why, Mrs. Isiga? Why do we need to circle prime numbers? Like, it seems like more work, and we're kind of like not wanting to do more work. I hear you. I understand. This is keeping us organized, right? Staying on track, making sure we're not doing even too much work. So between 3 and 4, we could tell 3 is a prime number. Now, why do we circle it? Because if we did it, we might just keep going. 1 and 3, 1 and 3, 1, 1, right? And we would be here for the rest of our lives if we kept going, giving all the factors of itself in 1, right? Now I gotta erase this. All right, so in summary, circle prime numbers. 4 is composite. We keep going. That's going to be 2 and 2. And now 2 is again prime number because if we kept going, 2 and 1, 2 and 1, 1 and 1, right? So we circle them just to remind ourselves we stop here. It's also important because now we're highlighting there are 3 prime factors for 12. All right, so we're done with the factor tree. We've circled the prime numbers. Step 2 is to rewrite and simplify or extract, all right? So we're going to start by putting the prime factors in order from least to greatest. I didn't specify that, but going from least to greatest, all right? So a smaller number, right, is going to be 2, and we can list it, we can do this 2 different ways. So we could list this in expanded form, and you could say 2 times 2 times 3, or right? Like what we learned from the last slide, right? Is we could rewrite it as exponents. That would be 2 squared times 3. So remember, our goal is we want our exponents to be even. I didn't specify why that is, so I'm going to do that here. So this radical, specifically the index is not given, but it's going to be 2. The index tells us like how many pairs we want to factor out to pull out of the radical. So how many pairs can be factored from radical? I know it's a lot of detailed notes. I want to make sure we're ready, when we need this. All right, how many pairs can be factored from the radical? So the index is 2, so basically we're looking for like a copy and paste. We're looking for 2 of the same term or same number, right, that's copied and pasted. So looking at our example, there's only 1 pair of a number, right, where there's 2, and it's the number 2. So what happens is one of them gets canceled and the other leaves the radical. So this would simplify to be 2 rad 3. Step 3 is to simplify. This is us simplifying 2 rad 3. That's going to be our final answer. I wanted to show you for this other method too. You can, again, 2 different ways. You can write it in expanded form, or you could write it with exponent with even exponents. Even exponents. Where we're specifically looking for even exponents. Let's say it was an odd number, like it was 2 cubed. You would still want to group, again, take that exponent minus 1, so 2 squared, and then just add the other 2. All right, so if it does end up giving you an odd number, we want to subtract 1 from it because our goal is we want even exponents. Why do we want even exponents, right? Because remember, we can just divide it by 2. This piece is really 2 to the power of 2 divided by 2, right? 2 divided by 2 cancels, leaves us with 1. So the 2 essentially leaves the radical, leaving us with 2 rad 3 as our answer, which you'll see we get the same answer. Methods, not that they don't matter, they're important, but you're deciding what method you want to do when you're simplifying. For the sake of this video, because we're probably, most of us are seeing this for the first time, I'm going to be showing expanded form. But again, like anything in math, as you get more comfortable and confident, you want to, upgrade, level up, and then you can try this even exponent method. But if you're struggling with this topic, right, you know yourself, you know where you're at, expanded form is going to be safe choice, going to be easier. Even exponents can be a little trickier, but if you're feeling solid on this, then it's going to get you the answer quicker. Expanded form has a little more work, but if you're starting off, it keeps it organized. All right, that making sense? Okay, we're gonna move on. Hopefully we are adding this to our notes, and I'll pause it so you can do that. All right, we got to practice on your own for Desmos, so I'm gonna skip that. All right, so these are all of the perfect squares and perfect cubes. Let me see if my spotlight will work. Nope, it's being weird today. My computer's not doing good. All right, so these are all of the perfect squares, perfect cubes. Ideally, you want to have the perfect squares memorized by now. We would want to start going into perfect cubes, but for our class, we might just touch on it, but we're not gonna go super in depth with the perfect cubes. But a cube root, the index is just 3. So, right, telling us how many times is that number repeated, right? If it's 3 times, like the top one, 2 times 2 times 2, when the index is 3, we would be looking for 3 of the same number, right? In that case, there are 3 2s, so 1 leaves the radical. Always 1 leaving. The other ones are always canceled. Okay, we're going to not spend too much time on this. Just this is something you'd want to memorize. We can add this to our notes too. We're going to move on. All right, our second method is for simplifying radicals is called the perfect square method. Again, as you're getting started, I feel like factor tree method is going to be choice, factor tree with expanded form. But as you're getting more confident with perfect squares, you're like, oh yeah, I got them memorized, then this might be the method for you. All right, we're gonna look at it. So method number 2, simplifying radicals with the highest perfect square. All right, step 1 is to list all non-negative or decimal factors of the number inside the radical. And we're like, we got this, because we've done this before in our, we've done this before for Cougar math skills, right? We're listing out all the different combinations we can multiply to get this number, right? So we start with 1 in itself, right? Again, this is how I do it. I start with like 1 in itself, and then I go down the line until we come full circle. So this is my method of staying organized. Again, if you have a different way of listing out all the factors, you do that. All right, next number after 1 is 2. And 32 is divisible by 2. It should go in 16 times. All right, next number is 3. And we're thinking, is 32 divisible by 3? Nope. So we're erasing. And we jump to the next number. All right, next number is 4. We're like, okay, is 4 work? 4 times something gives us 32. It does, 8. All right, next number would be 5. But 32, it's not ending with a 0 or a 5, so 5's not an option. 6, well, 3 didn't work, so 6 can't work. 7, nope. So we come full circle. These are all the combinations, the ways that we can multiply to get 32. Okay, so thinking back on perfect squares, what we know about perfect squares, do we see what the highest, the largest perfect square is here in this list of numbers? If you see it, go ahead and let me know in the room chat. What is the number? What is it? What could it be? All right, answer in the room chat and we'll go over it. All right, so our highest factor is going to be 16, and we'll box it. 16. It's not 4 because there's a larger number, 16. If you did choose 4, eventually you would get the same answer, but you'd have to do more work. So this is, for this method, we're trying to do the least amount of work as possible, looking for the largest perfect square in our factors. Okay, so 16, if you recall, 2 times 16 gives us 32. All right, step 2 is to rewrite this. So we're going to rewrite it out, listing out all that's inside the radical. Again, you can still do that other method with changing it to be an exponent, right? 16 is 4 squared, but for the sake of this video, we're doing expanded form. All right, so 2 times 16 times x to the power of 4. So remember, our goal is looking for perfect squares, all right? Perfect squares. We know that 16 is a perfect square. We know that 16 is really saying that this is 4 squared, right? 4 squared. Index is 2. We're looking for pairs of the same number. Basically, we're looking for even exponents here. And we can see we've got a couple. We've got 4 squared, which we know is going to end up giving us 4, right? Because the exponent cancels. And there's also this x to the 4th, which is even. The exponent is even. So that's also going to end up leaving the radical. If we need to do some side work here, we can. Our side work would be the exponent divided by 2, right? 4 to the power of 2 divided by 2 is going to be 4 to the power of 1, or just 4. And then x to the power of 4 divided by 2 is going to leave us with x squared. So these are coming out of the radical. They're being factored. Half of them are eliminated. The other half is leaving the radical. All right, so that would leave us with our coefficient 4, and then x squared rad 2. And that would be our final answer for this one. And I know for this one, I might be going a little fast, and 2, I'm sure the variable threw you off. You're like, wait a minute, there's letters now. I know it's getting more complicated now that we're in high school, going a little step up, adding in some variables and coefficients, but same process. If it's easier for you to split it up, you absolutely can. You can just separate them and then just make sure that your final answer is like merging the two families together, and then they box your answer. But you could have sorry, that was x to the 4th. You could have absolutely done this. If it's throwing you off being together, separate it. Just remember they're being multiplied. All right, so we'll add this to our notes. Again, if you have any questions, let me know. Do we have any questions? I'll take a pause for questions while you're adding to your notes, and then I'll answer them in class. All right, this next one you're practicing on your own, so we're gonna skip this. All right, and that was the end of our video. Again, any questions, let me know. If you're watching this as a recording, let me know. Any questions, email, text. All right, bye.